Hello guys, today we will talk about the thermal shrinkage testing of battery separator. So thermal shrinkage is shrinkage caused by the heat, either due to the internal heat of the battery or due to the external or environmental temperature. So when heat increased from a threshold limit, then this separator between anode and cathode may shrink. Once it shrinks, it may cause a short because anode and cathode may touch each other physically. It will lead to the fire. So it's very important to understand or investigate the thermal properties of his battery separator. So thermal shrinkage testing matters a lot because it's very critical for safety and prevents the internal short circuiting during battery overheating events. And it also impacts on the performance when you are charging your battery at high C rate or in very short times, or your battery or device is subjected to the abuse conditions. And we need certifications before we use this separator for the battery operations for the on the commercial level. So this failure of separator or shrinkage may cause huge fire. So if your battery is installed somewhere in your home, it may burn your home. If it's in the car, it may burn your car. So what is the testing methodology to measure the thermal shrinkage? There are standard reference methods like IEC 62660-2, which is normally used for the EV batteries to test their thermal shrinkage. And UL method is also commonly used method. But today I will show you how to measure the thermal shrinkage in labs inside the research institutes or universities. So the photo is just rolls of different polymer separators. So the test procedure is very simple. First you have to take the piece of your separator, and you can cut your separator into circular dimensions like 25 mm diameter, and then you have to dry your sample. Make sure there is no moisture. So you can dry these samples at certain temperatures, and the drying temperature depends on your material. If it's polymer, its drying temperature is low. If it's ceramics, which is made up of metal oxide, then you can use the high temperature. So, but this is optional step. So after cutting the samples, you can expose or place the separator, your sample, between glass plates to prevent the curling. So then you can put these glass plates with separator sandwiched inside the oven, and you can heat the oven at, for example, if you want to investigate at 90 degree, then you can keep your sample at 90 degree in the oven for at least 30 minutes. But I suggest to use the 1 hour to make sure it's completely thermally shrinked. So you can heat them at 90 degree. Then you can choose another piece of samples at 120 degree, and then you can choose the third piece of separator at 150, and similarly you can take the 3 pieces of each separator at different temperatures. So once they are heated, then you can cool down and bring them out, because you have to compare their size. Initial size is 25 mm diameter, and then you have to calculate their length or width or even area to see the difference. So there is a very basic, very simple formula which can be used to measure the thermal shrinkage percentage. Some people use the area, like initial area and the final area after heating. or you can use the length and width. It all depends on you, because you have to just compare with your reference materials. And for example, here L0 represent the original dimensions, length or width. It can also be area. So LT is the dimension after heating. So after you heat, for example, at 90 degree, then you have to measure their area again. And then you can use these equations to measure the thermal shrinkage. So I will show you some photographs of separator which I have done. So for example, this is PP, PE and PP tri-layer separator. I measured their thermal shrinkage as 25 degree, 120, 150 and 180. At 180 it almost disappears. And on the other hand, I have some other samples. I also measured their thermal shrinkage at different temperatures. You can see these photographs. From top, where is 25 degrees centigrade, to the bottom, which is 180 degrees centigrade, you can clearly see there is a change in the area of the separator. This is called thermal shrinkage. So based on these photographs and calculations, I have measured the thermal shrinkage percentage and draw the graph. You can see the cell guard, which is PP, PE and PP, tri-layer separator. It shows the highest amount of thermal shrinkage when we increase the temperature above 120. And its thermal shrinkage at 180 degree is about 80%. Compared to this cell guard, my separator shows the lower thermal shrinkage. So this is the way how you can measure the thermal shrinkage of your separators and draw a graph like this for your journal paper, for your thesis, or for your presentation. So let's dig more. How we can interpret these results? So first is test temperature, target shrinkage, and interpretation. So if the heating temperature is less than 90 degrees centigrade, and it should show zero thermal shrinkage, which is ideal and it's required for normal operations. We should not expect any shrinkage. And if the temperature or test temperature is between 120 and 150 degrees centigrade, then the ideal thermal shrinkage should be less than 5 to 10%. If it's higher, then it's not good for the battery. And good thermal stability for the moderate thermal events. And if we test the temperature at 150 degrees centigrade, and ideally the thermal shrinkage should be less than 15%. Or it also depends on the material dependent threshold. It can vary by changing the material, like from PP to PVDF, like this. And the test temperature at 180 and 200 degrees centigrade, the ideal thermal shrinkage should be less than 20%. And because this is very important, when there is a like abuse condition, accidents, or these kind of stuff, then this shrinkage, if it's greater than 20%, it's very dangerous. Lower thermal shrinkage percentage indicates better thermal stability and improve the safety performance during thermal events. Thermal events means if you are using the battery at very high temperature, in hot weathers, or some abuse conditions. So material performance comparison for different kind of separators. Very famous material is polyethylene, and it have very low thermal stability, like it's around 120 degrees centigrade it start to shrink. So it's only used in low cost applications. On the other hand, if we talk about the metal oxides or ceramic coated separators, then their thermal shrinkage or thermal stability is less than 2% even at 200 degrees centigrade. And they are normally used in the EV applications and aerospace. And another very commonly used separator is polypropylene, which is a moderate stability up to 160 to 170 degrees centigrade and used in standard consumer electronics. So most of our electronics have some batteries, and inside the battery the separator uses PP. And lastly, another kind of polymer very famous is also PVDF. It have high thermal stability above 180 and to 200 degrees centigrade due to its high melting point. So this is used for premium applications required thermal resistance. So these are the different materials used for the battery separators and their thermal shrinkage and their applications. So the key takeaway and implementation is testing the separator comprehensively. Evaluate the separator at multiple temperatures to understand the full thermal behavior profile. If you are going to use the separator for your battery application, you have to understand its thermal stability. Very important, especially for the people who are working at elevated temperatures. And consider both directions. Like separator is made in both machine direction and transverse direction. And the shrinkage in both sides is very important. And thirdly, you should pay attention to the material selections. As I said, that PP, PE, PVDF, each kind of separators have different thermal shrinkage due to the melting point of the materials. So that's all for today, and we learned how we can measure the thermal shrinkage of battery separator and why it's important. Thank you very much.